Right. Now let's look at another LeetCode problem. This is 572, subtree of another tree. Given the roots of two binary trees, root and subroot, return true if there is a subtree of root with the same structure and not values of subroot, and false otherwise. A subtree is a binary tree A subtree of a binary tree is a tree that consists of a node in tree, and all of these nodes' descendants. The tree could also be considered as a subtree of itself. Examples. Alright, let me read the problem description to see if I have any questions. We are given two binary tree, the root and subroot. So we need to check whether subroot is can be found in the root. Okay, so some examples. Examples 1, we have 3. On the left we have 4. To the right we have 5. And then the left subtree we have 1, 2. Subroot is 4, 4, 1, 2. So this will return true because we can see there is a subtree in it. Now examples 2, we have 3. So this is basically the same as examples 1, except that the 2 has a 0 in there. Okay, subroot is still the same here. So here this would return false. Because there is a 0 at the end. Alright, I think I understand the problem now. I would like to ask some clarifying questions. First one is root and true. I would like to know whether I can assume that the root and subroot are non-empty. So we are given that the number of nodes in the root is between 1 to 2000. And then the subroot is from 1 to 1000. Okay. Alright, I think I got the question now. I got the problem now. Let me explore some possible approaches. Alright, I think another clarifying question is whether we need to differentiate between left and the right child if there is only one child. Okay. Okay, here I'm gonna assume the answer is no, for simplicity as well. So for these questions, I can think of a brute force approach, which is we are gonna traverse the left and right, and then at each point, if we found that the value, say we start from the root of p of the root, then we check if it is the same as uh, the root of subroot, and the subroot, then we use it at the basis, and then we could check it recursively whether they are the subroot is indeed inside. It's a subtree of the root. If it is not, then we continue. Then we continue the root with the child, and then we do the same, meaning that we check whether this child, any of the child, match with the subroot, and if it is, then we do the same checks that we did in the root, and we did the same checks that I mentioned earlier, which is checking all the children between the current node in the root, the current subtree in root, and also the subroot. I think that could work, but I'm thinking whether this could be too costly in terms of time, because there could be many matching values with the subgroup. Okay, I think I've got some idea. Hold on. So I noticed something that I think what is interesting is that the depth of the subgroup. Hold on, actually not. That's not true. So I was about to say that the depth of subgroup will be the same as the depth of the subtree, but it doesn't mean that the subroot will start at the same depth as the root. Okay, so that is an observation, but I don't think that's useful. So findings number 1 is subtree depth is equals to the subroot depth. Okay. So I'm thinking that if we could invert the tree and then traverse it from the bottom instead. Oh, actually, no, it could be too complicated if the subroot gets too deep. Okay, so how are we gonna do this? So in the first example, I think our brute force approach can work. We see that 4 subroot begins with 4, but the root begins with 3, so it doesn't match. We move on to the third node, and then we see there is 4. Then we continue until the child. We have 1 and 2. We match with the subroot. So then that will return true. Then there could be many possibilities, and this problem could be very time consuming. Thinking that if there are 2000 nodes, all of the same values, and then the subroot is of 1000 nodes, then if we need to check all of the roots, then it would take O n times m, which is 2 million. I'm wondering if that would cause a time limit exceeded, but I could not think of any optimizations right now. Okay, so how about if I have the value of R1 in a complete binary tree, and then the subroot would just be like one node, then it means that I'm checking for all nodes in the root. So that would be O and M. Okay, so 2 million seems good. Okay, so I'm thinking if there is a better alternative here. So what if I let me think of some possible optimizations. So I'm thinking that if I have checked the at a point, I found that the current node in root is not gonna be the subtree. That is the same as subroot. Then how am I gonna utilize this information? Is it gonna be useful to me? Let's see. I think it's not helping at all. Yeah, but the children of that node could be subtree that match with subgroup. So we need to check that as well whenever we encounter a children node that match the subgroup. So I cannot think of a better way than the brute force one here. I think you just go ahead with it. Does it sound reasonable to you? I would like to start programming unless there is a further optimization that you would like me to explore. Okay, I would assume the interviewer say no, then let's get started. So we are given the each subtree that we need to implement. Subtree treat the root and subroot. So what we need to do, I think I need to use another helper function to check whether the current node could be the subtree that match with subroot. Right? Yeah, so let's do that. Well, we're gonna do this. Alright, so I think I'm gonna create a helper function there. But let's just start with the given function. This one is subtree root. So I'm gonna check here. I'm just gonna do let's see. Okay, I'm gonna create another function later. This will be return. I'm gonna call the function check root and subroot, and is subtree hold on 1 second. What I need to take care whether there is a child or not. Do I need to do that? Let's see. Okay, I think I don't need to do that. Okay, let me think for a second. If I call it the check at every point, so I need to take care of some cases there. Okay, let's see. So cur is check root and subroot, and left gonna is subtree root dot left comma subtree, subroot. If root dot left else false. And then same for the right one. The I'm gonna return curve and left and right. Okay. So now we need to create another function. Let me do it in the next page. So define check the root and subroot. First of all, well, this is actually the same as the previous one that we had and the previous question that we had. But let me just go to it again. So if not P and not Q, I'm gonna return true because in this point, both of them are null pointer. Okay, and if just one of them is non-empty, so here's a Q, then I'm gonna return false. Because at this point one of them is null and pointer and then one of them is not. Else I'm gonna check p dot false is q dot false and check again the left and right and check also the right one. Sorry, this should be left, right. I'll just call it P and Q. Okay, so I think this should work. Let me quickly walk through the code again to make sure I haven't missed anything. First of all, I check the actually I need to use all of them. So I check whether the current root could be the subtree or the subtree, and then I'm gonna recursively check the left and right children. Okay, so I'm gonna check also recursively check the left and right. if there is a child swimming of it. If no, then where there is not a subtree for it in the chart. Okay, so the check, what I'm gonna do is see if P and Q are both null pointer. If they are, then good. We have a matching tree structure and value. And then in the other condition, we may have a case where one of them is not a pointer, but the other side is a tree knot, which is false. Then in the end, in this case, in the end, I will have the case where P and Q are tree knot. So what I'm gonna do is we will check whether the value are the same, and then go to the left and right child to see if they have the same children. Okay, so I think that would be it. Now let's test the code with the example input that we are given to see if it works as intended. In the first example, we have 3, 4, 5, 1, 2. So the subroot start with 4, which did not match, which is not the same as the current one. So we go on to the left. And then we see that in the left, actually I think that is a minor optimization that we can do here. So at every step, for example, instead of storing all the chat into a variable, we could do if instead. So if, let me just cross out one of them. So if chat root subroot, then return true. Okay, I think this is a very minor improvement. Or we could just put it all into one statement, but I'll do it in the code later when I submit to LeetCode. But let's go back to our example there. So we have 4 and our long subroot start with 4. So we go to check function and we see that they are matching. In the end, it will return true. So that would be our answer. And then in the second example, we see that there is an extra 0 tree knot. In the end, it will return false because of it. So I think this should work now. Let me try to put it into the code. Okay, so we have turn check root and subroot, or a subtree left and right. Actually, just think of something. So in the beginning, it's just a bit messy, so I think this would be better if root, if not root, or not subroot, and each return false. Okay. Otherwise, it could recurse the check, recurse the function. So then we explore the left and right, left and right now. Okay, now we are done with it. So now let's implement the check. We have enq. And so to save time, I'm gonna pull out our answer from previous question because they are basically the same. Alright, so it's called SM3. Yep. So we try to run it in our test cases. We got it wrong. Okay, and why is that? If not root or not subroot, return false. No, that is not the case there. It will check if same tree, the root and subroot. It's just not. Then we do an OR with the left one. Okay, so the subroot should not change into the left. Yep. Wait a minute. I think I don't need to check this thing. So if not root, return false. Okay. Now let's test it. Error. Yeah, I think I don't need to do this thing. Let me just delete the type checking. I'm not sure if that is the cause. Interesting. Subtree error return. Okay, what went wrong here? So it's saying that this type error string return plus is not valid variable except the type boolean. But I don't put any boolean in there. So what is this about? Subtree root and subroot P and Q. I don't see why there is an error here. It says in line 54 in driver solution. I don't even have a line there. Let me put it on full screen. Okay. Is it the name? Let's check here. Oh, okay, I got it. So I forgot. Okay, so I don't copy the whole thing there. Yep, I missed it. Okay, so let's see this. The typo. Yeah, so we got it right. Now let's try to submit it. Hopefully we don't get time limit exceeded. Yep, we did complete the job here. Very good. Let's look at the people's solutions. So this one is using DFS. Okay. Yeah, I think this is iterating through possible all of the possible answer as well. Let's look at another solution there. And this has a larger pool. Subtree Subtree itself dot serialize subtree, and is this even allowed? Like okay, you're serializing. I think this is quite interesting. Let's see what it's doing. Step root snack, pop. Okay. I think this is like in order or something, and then tries to check if it is in it. Okay, I think that might work, but yeah, I think it's about the same complexity. Anyway, I think we are all mostly doing the same thing there. Yeah, I think there's no other way other than we need to brute force it. I think we will stop here. Thank you, everyone.